would like to do is to go to a new chapter. This new chapter is non-equilibrium phase transitions. And one classic of these non-equilibrium phase transitions is what's called directed percolation. It's a universality class in very much the same sense as the Ising model is a classic for equilibrium transitions. This is the universality class for non-equilibrium phase transitions. There's no pointer. So what this model is, it's a lattice gas model. And that's different now from what we did over the last weeks, where we looked at continuum models. So here you have a lattice. And it's put like so, like a square lattice turned by 45 degrees. And there's several processes that go on here. It's just one species A, and this one species A can hop between different sites. That's indicated by the D here, so it can hop from right to left or left to right. Then it can actually decay or die. This is a process here that happens on the second path from the right, where you have 3 steps to the left, and then the particle dies. There's also a creation of offsprings. A goes to 2A, and there are several instances where you see there's one individual and then it branches off to 2 individuals. There's also coagulation, so if you have 2 branches, they come together and form just one branch. You can think of this as this kind of stochastic process. You can think of this also as a percolation problem where you trickle through a porous medium. And the question there typically we ask is, depending on the parameters like the birth rate, coagulation rate, etc., when does there exist a continuous path connecting the top to the bottom? So when does the system percolate from top to the bottom, like in a percolator when you make coffee? Okay. And let me first give you the mean field idea of that. And then we go and transform these lattice gas models to path integrals. And then later on, I'll show you how then this modifies the behavior of these systems. All right, so this is a new chapter. It's called lattice gas models. It's not a gas. It's just the name people gave to these kind of models. It's an interacting lattice system. That's the proper name. So let's start with directed percolation and do a mean field analysis. And mean field here means I'm neglecting all kinds of fluctuations, and I'm also treating the number of individuals here as a continuous real variable and not as a discrete variable. So let's say n of t is the number of A particles at a given time t, and I'm assuming that this is a real variable, and it includes the plus, and it also includes the 0, and 0 means it has died out. Okay. So as I wrote it down, so let me repeat it here on the blackboard as well. It dies with a rate alpha 0. It creates an offspring with a rate alpha 2. That is birth. And if 2 come together, that's kind of a competition effect. They compete for some resources. That's the picture behind that. And then with a rate beta 1, you have just one individual A left. Okay. There's also diffusion, but let's just look at the reactions alone. And then let's write down the mean field equation. It's basically translating these kind of reactions into a rate equation. So what do we have? if there is a number of individuals present in the system, then there is a creation of new individuals with rate alpha 2, and there is death with rate alpha 0. And that means we have here a positive contribution from birth and a negative contribution from death. On top of that, there is a process that penalizes the presence of too many particles. And this happens if two come together. That's proportional to the density squared. And then you reduce by rate beta 1 to 1 less. So that's minus the rate times n squared of t. Okay, so from that, you can ask yourself of what happens as time goes to infinity. So what's the steady state of that? Well, that depends. If this here is positive, then the population will grow. As it grows, there's at some point a high enough population where competition matters, and then there will be a balance between the two. On the other hand, if this is negative, then the population will die out to begin with, and this doesn't really help because it's also a negative term. So that means for delta, defined as the difference between the birth and the death rate being negative, we do have n going to 0 as t goes to infinity, and that we call an absorbing state because there's no way to get out of that state, right? There's no process. If you look here, if there's no individual present, nothing here generates a new individual. Right? So that's a absorbing state. In the other case, so for delta being positive, as said, there will be a balance between those two terms. So that means in this case, you will have n going to the ratio of that, which is then delta divided by beta 1. And that we call a active phase. I don't mean this in the sense of active matter. This is just the same name that has been picked here. It's a phase which is active in the sense that there are particles present and the system is not in a dead state. Okay. So you see there is a phase transition already, and this phase transition happens at delta equal to 0. And this phase transition is called a absorbing state phase transition. It's different from a order-disorder transition like you find it in an Ising system. In an Ising system, there's action kind of in both states, despite the fact that the magnetization is 0. It's not a dead state. It's a thermodynamic state where the average of the magnetization is 0. Here, this is really a dead state. There's nothing fluctuating anymore here. There's no particles and there's no fluctuations. So let me now characterize that transition in a similar fashion as you would do in a mean field analysis for a ferromagnet. So let's solve the equation of motion, n of t. And luckily, if you look at that equation, it's simple enough to find an exact solution. I'm not going to show you how you do this. you can just check that this is true. So this is the initial state. This is what I call inactive. N naught is the initial density. So n at time equals 0. And then the exact solution is this. It's n naught times n active, n naught plus n active minus n naught, e to the minus delta times time. Okay, and when you look at that, what happens as t goes to infinity? As t goes to infinity, this second term in the denominator vanishes, and all that remains is n naught times n active. N naught cancels, so this approaches n active in the limit of asymptotic times. You also note that the relaxation to that state is exponential. Right, so relaxation to the steady state, n active is exponential, and it has a time scale, and this time scale I call T relaxation, that is equal to 1 over delta, as you can read off here, right? And that means that if I write this out, this is 1 over alpha 2 minus alpha naught. So if you fine-tune the birth and the death rate in such a way that they equal each other, then these relaxation rates go to zero, go to infinity. Okay, so this goes to infinity at the transition, and that means you have critical slowing down in the same way as you have critical slowing down close to a thermodynamic phase transition. You can also check what happens here at this point. So at delta equal to 0, you can solve the equation also exactly. It's not harder than the other one. And what you find is then that the relaxation is like so. Beta 1 n naught times t. And that means you have an algebraic approach. This goes like t to the minus 1 as t goes to infinity. So you no longer have exponential relaxation to the steady state. You have a power law relaxation. Okay, now let's define critical exponents. And here we follow the same logic and reasoning as one does for thermodynamic problems. You want to know how does the order parameter change in the ordered phase as you go away from the critical point. So what is the change of the active density and active as a function of delta? Well, that's easy to calculate because this is just this delta over beta 1. In general, if we were to account for fluctuations, which we don't do yet, you would have something like delta with an exponent beta, generalizing the result that we have in mean field. So here in mean field we have beta equal to 1. So not a half like you might recall from the Ising model, but beta equals to 1. Okay. You can also define a dynamic exponent. But a dynamic exponent is usually defined in relation to a correlation length, like so. So as the power with the correlation length psi, z minus z is the exponent characterizing the relaxation. I haven't defined yet a correlation length, right? We can do this in a minute. That correlation length, also by definition of what the exponents are, is supposed to scale like delta to the minus nu. Okay, so here we kind of can insert that. Then you would have T relax is proportional to delta to the minus nu z. And that's what we already calculated. We have delta relax 1 over delta. And that means for that exponent, for this combination of exponents, we know that this is 1. Again, in mean field. What about the correlation length? Well, for that, we need to extend the model. To include diffusion or space. And that's not hard either, right? Because we already have the equation describing the reaction kinetics. And all we need to add is that this is a diffusive field. That means the equation you would get is dTn of x and t is all the reaction terms. So birth minus death minus beta 1 n squared of t. And then I just add plus d nabla squared n of x and t. And here in the same way, those are functions of space and time. So now that you have this, okay, so from that, we can actually figure out what the relation between correlation length and time is. It's a diffusive process, so we know mean squared displacement goes like time. So correlation length squared should be the relaxation time, or in other words, we have for this mean field model that any kind of length scale here has to go like the inverse of the corresponding time scale. So if we talk about the critical quantities, the correlation length and the relaxation time, they need to be related by so. And that means as delta goes to 0, this is delta to the minus 1/2. And then we can collect terms. We have beta equals 1. We have nu times z equal to 1. And we have nu equals to 1/2 from this here. So nu is equal to 1/2. And z is equal to 2. And the 2 really here is just that you have diffusion. There is a nabla squared. This reflects directly that the exponent set is 2 for this mean field model. Okay. Good, so that's what you get in mean field. And now let me just shortly say what the relevance of that is. In the Ising model, you know it's a universality class that's related to the up-down symmetry of the Ising model, right? And it has a scalar field with the up-down symmetry, and that's the Ising class universality class. Here, there's a conjecture that all absorbing state phase transitions with a single absorbing state are in the directed percolation, or short DP, universality class. All right. And that seems to be true actually rather generally. All right, now that we have that, we do need a corresponding field theory to deal with that. And I'm going to show you now how you do that. And maybe we shortly recap what we already had. So we need a field theory that accounts for fluctuations. So that means basically when we have a master equation, which is a description of that process when you write it in terms of probabilities for the raising and lowering of the particle number and for the hopping between states, I want to have a mapping of this to a field theory, and this means we need to have some kind of path integral representation of these master equations. And this is now a really cool topic, because in quantum physics, you know there's a correspondence between the Schrödinger equation and second quantization. And there's field theories you can formulate on the basis of second quantization called coherent state path integrals. And here you have the same kind of analogy. You have the master equation being a second quantized form of your dynamics, and now you want to rewrite this quote, quote, second quantized form in terms of a path integral. Let me, before we go there, remind you of what we had for other path integrals. So recall, and we need this on the board, that we were discussing for a particle the following general form of a Langevin equation. This is all vectors. I'm just writing it without vector indices. So this is a Langevin equation with a state-dependent amplitude in the drift and a state-dependent amplitude in the noise. Okay, it's for a particle or a vector x that we looked at. You know this Langevin equation you can write in different forms. So let's think of this in a Ito sense. And then you know that this kind of Langevin equation is identical in content to a Fokker-Planck equation, right, where you have here the drift term, gradient dotted into the drift vector. And now I have to write the indices plus a half di dj bi bj p of the arguments. And we know that there's a relation that this B equals C transpose. And for that class of models, right, so for these Langevin equations or Fokker-Planck equations, we have seen that there is a path integral representation of the following form. You consider a path from x naught to x final. Then you have to integrate over the fields and the conjugate field that we called Q. Later on with fields we call this the response field. And that's e to the minus action S of x complex unit IQ. Okay, and the action that we calculated is an integral between the initial and the final time. And it contains two terms. There's one term which encodes the equation of motion. So that's IQ. Then you have dtx minus a of x. Right? And if that would be it, then this path integral that you have is just a delta function representation. And the solution would be the most likely path, the classical path, which is the solution of the deterministic equation. You don't have quite that. You have here a part coming from the noise. And this is complex unit transpose B of x IQ. And that's coming from the noise. And this is coming from the drift. And you can really think of this in a very similar fashion as you would think of a quantum path integral. In the quantum case, you have a classical path, and you have quantum fluctuations. Here you have a mean field path without any kind of stochastic fluctuations. And the second term here comes from the Langevin noise that you have here in the Fokker-Planck equation or here in the corresponding Langevin equation, and it smears out the classical path by the noise amplitude that you have. Yeah?
So that's P of x final at T final.
Oh, yeah. Yeah. Thank you. Okay. Okay, so that's as a reminder. And now let me give you a kind of an appetizer for how this works. And I'll call this the spectral method for the linear death process. Okay, you all know the linear death process. You have particles of one type. They decay at a rate A going to 0. So A goes to empty with a certain death rate that we call lambda. The corresponding equation for the probability distribution, so the master equation for the probability of having n of particles A at time t is lambda times n plus 1 p n plus 1 t minus lambda n p n t. So you gain into state n if you start at state n plus 1 and you die, and you lose from state n if you start in state n and die and go to state n minus 1. Okay? Now, I guess we have studied versions of that in the early exercises, but let me define now a generating function which is p of n and t x to the n. Okay. And we know what those objects are. You can generate probabilities once you know that generating function, because the probabilities are the Taylor coefficients of the generating function g of x and t. That's one way of seeing it. Another way of seeing that kind of formula is, say you're annoyed by the fact that you have discrete variables, and you don't like to deal with objects where you have a differential difference equation. You would rather like to have something that on the right-hand side has a continuous variable and you have a differential operator instead of a difference equation that like you have here. Then this might be a recipe of going from a discrete variable, n, to a variable x that's now a real number. Okay? So let's see how this works. If you write down the master equation for that, and that's a straightforward thing, you just take the time derivative of g, you use the expression for g that you have here on the right-hand side, you pull through the time derivative to act on p of n and t, you insert the equation of motion that you have here, and then you shift indices, and you get an equivalent form for the equation that defines the time evolution of the generating function. So, and this is what you get. So as promised, you now have a differential equation in a dual variable x instead of n. And that has a structure which is minus a linear operator acting on g of x and t. Okay? And I call it h to remind you of similar constructions that you have in quantum physics. The key point, though, only is that there's no quantum feature here. This is just the fact that you have a linear equation and the object that you have in front of g is a linear operator. So that's all you have. H is a linear operator. And once you realize that this master equation can be written in an equivalent form that corresponds to a spectral problem, you can now do the spectral analysis of this equation, right? It's a linear operator, so you can find the eigenfunctions for that. So let's say h psi j of x is lambda j psi j of x. That's my eigenvalue problems. And of course, I have to now calculate the eigenvalues. I have to calculate the eigenvectors. I'm going to show you how that works. And but for now, let's just say we have that. So let's say we know that there is these eigenvalues and eigenvectors. Then, if you have them, you can write the solution as the initial values, which I call Gj of t, psi j of x, so standard expansion of the general solution in terms of eigenfunctions. Okay, and that means then we have T j of t is lambda j of t. And this is solved by exponentials with initial value Gj0 e to the minus lambda j times t. So in order for that to be a meaningful solution, we need that our probability densities are bounded, right? They cannot explode because we have normalization. And that means if we look at the spectral problem here, there's a constraint on the spectral problem to be a well-defined solution, namely that these eigenvalues need to be non-negative. If they are negative, this would be actually an exponentially growing term, and you would no longer find a bounded solution. So boundedness of the solution implies that they are non-negative, the eigenvalues. Good. Now we are left with solving this kind of eigenvalue problem. And now let me define operators to solve the eigenvalue problem. In a way that I'm basically exploiting the fact that I need to have a bounded spectrum. And I also want operators that help me finding solutions for different eigenvectors once I have found solutions for particular eigenvalues. So I want to somehow be able to connect different eigensolutions. And let me now just define two objects. One is dx, and the other one is defined as x minus 1. Okay. And if I do it like so, then I can write my operator, the linear operator, as lambda at a dagger a. If you look at these two operators, a and a dagger, right? So you have a times a dagger applied to a test function, and you do the reverse. Then you see you have dx acting on x minus 1 and the test function, and the reverse. This doesn't commute, these two operations. And when you do the algebra, this is 1. So the latest here, you should notice that this is the same construction, or same spirit of construction, as solving the eigenvalue problem of a harmonic oscillator. And the deep reason is really that this is a linear spectrum, and it's a bounded spectrum. And for linear operators of that type, this is a construction method which works in general, and doesn't really have to do anything here with the fact that the system is quantum. It just means that you can calculate the spectrum of linear operators. All right, now, how do we do this? Well, we can write, it's like in quantum physics, we can ask ourselves, what is the eigenvalue of a eigenfunction on which a dagger is acting. So this is just standard algebra. Using the commutation relation, I'll get this. Now using that as an eigenfunction, this is lambda j plus lambda times a dagger psi j of x. Or of course I can write this as lambda j plus lambda a dagger psi j of x. So what you find by doing so is that this object here is again an eigenfunction. As you see here, it's reproduced on the right hand side, but the eigenvalue is shifted. The eigenvalue is lambda j plus lambda. You can do the same game by asking what is the eigenvalue for the object a times psi j of x. This is done in various ways. Either you solve it in the same way as I've shown you here, or you use the commutation relation between h and a. But in the end, what you get is that this is also an eigenvalue, but now it is shifted down. So a dagger and a are operators that raise and lower the eigenvalues by the amount of lambda. Lambda, remember, is the rate of death. And here we now come to the point where we need to use that the spectrum needs to be bounded. For the spectrum to be bounded, I cannot repeat this ad infinitum. This must stop at a point such that A acting on the ground state is 0, because otherwise I'm getting negative values. So boundedness implies that we must have a lowest eigenvalue, lambda naught equal to 0, with the eigenfunction being such that A acting on psi 0 is 0. But then, right, if you have that, then the eigenvalues that we get are just j times lambda, with j being from the natural numbers including the 0. So you have a discrete spectrum starting at 0, and our operators a psi j is really just psi j minus 1 x, and a dagger psi j is psi j plus 1. Yeah, I don't think yes. Okay, and this is our choice of normalization that we take by using this kind of rules for A acting on psi and A dagger acting on psi. It's not quite the same, right, as for an harmonic oscillator, but the difference is only that we have chosen a different kind of normalization, that we want this to be the J and this here to be the 1. Okay, and then once you have that, you can also easily calculate the eigenfunctions. So for the eigenfunctions, we have x minus 1 dx, that's the linear operator that we have, psi j of x needs to be j psi j of x. That's what we have, right? This is the eigen vector equation. Well, I can just we write this as dx psi j of x equals j divided by x minus 1 psi j of x. And that's solved by the function psi j, which is proportional to x minus 1 to the power j. As you might check for yourself by taking the derivative, you get the j in front and you get an extra factor 1 over x minus 1. All right, so we know the eigenfunctions. We need to know the initial values for that. So for the initial values, we just write out what the generating function is. It's sum over j. Initial values for the generating functions, exponential decay. And here are the eigenfunctions, x minus 1, j. Then we compare with what you get at time equal to 0. Okay, for time equal to 0, we have to go back here to this explicit expression for the generating function. When I put time to 0, I get the probability distribution at time equal to 0. And I'm fixing here the system such that there's a definite initial state that's n, a capital N, right? So I'm saying here at t equal to 0, we have n particles present. Then this here on the right-hand side is just delta n capital N, x to the n. So what you get is x to the capital N, where n capital is the initial number of particles. So from that we conclude that x to the n equals to sum over j x minus 1 to the power of j. Okay, so what would you conclude from that? For that, you have to kind of remember that there's a binomial formula, right? And that you can write a sum like that, like x to the n, using the binomial formula. So from here you can read off that the j of n are given by the binomial coefficients for j less equal to n and 0 for j larger than n. That's a bit of a tricky part here in the analysis. But then once you have that, you find that the full solution is the sum over all different states that you have in the system. Then your initial values, meaning the binomial coefficients, e to the minus lambda jt, x minus 1 to the power j. Right, and here you can again use that we know how binomial formulas work. So this is the same as 1 plus x minus 1 e to the minus lambda t to the power n. So remember here that lambda j is j times lambda. And that here I can write as 1 minus e to the minus lambda t plus x e to the minus lambda t to the power n. If that's my generating function, that's what you get. Now you either know from other means that this is the generating function for a linear depth process as we calculated it earlier, or you say, I want to actually derive those Pn of t's from that general expression. You can do this in a cumbersome way by taking all the derivatives if you like, but you can also notice that this object that you have here, you can again write as a binomial sum. Now, sum from n equals 0 to n out of n, 1 minus e to the minus lambda t, n minus n, x to the n, this is the second term, e to the minus lambda nt. Okay. And now you can directly read off what the probability distribution function is. So from that you see that now p n of t is this binomial expression. It's, you have to take n out of n, and you have this product of 1 minus e to the minus lambda t n minus n, meaning of not dying, and e to the minus lambda nt, which is the probability of dying. And that's another way, as you know, to derive the probability distribution function for a linear depth process, where you just argue at time t, you must have, when you go from end to n, you must have gone there by the death of n minus n, by the death of n individuals, and you have to remain then with the population size that's n minus n. All right. The questions?
Yeah, we solved the same problem some months ago, right? And
yeah.
Not with the spectral method.
Yeah.
What did we use again? It was a bit simpler.
You did do something else, which I don't recall either, because you did in the problem set, right?
Yes, I think so. So I remember we got this, but we got it a cheaper way.
It's not about cheap.
Yeah, no.
This is not the point. It's a very expensive way of doing so. That's not my point. It's not, I'm not suggesting that in writing and solving these problems you should always try and find ladder operators to solve them. That's not the point. There's much cheaper ways, and the cheapest way is actually to argue the solution. Right? This is very straightforward to actually get the solution in one line without even having to do any kind of calculation. So the reason I did this was to teach you that an equation, which is a master equation, can be formulated as a corresponding differential equation in a continuous variable x instead of a discrete variable n, and that solving that equation invokes the concept of ladder operators, raising and lowering the indices, and that this is analogous to the corresponding quantum logic, where you also have a correspondence between first and second quantization, and this correspondence is via these raising and lowering operators. And in quantum physics, you can exploit this even further for field theories and derive field theories using a representation of your many-body quantum system in terms of raising and lowering operators. There's a whole slew of things you can do in quantum physics with these concepts. And what I want to show you here is that it's mathematically equivalent here and in the case of stochastic processes. And the reason is not quantum physics, the reason is that these systems are linear operators, and you can switch between a discrete and a continuous representation. And as you switch, you naturally have things like raising and lowering operators turning up. It's a motivation for what we do after the break, namely to show you how you write down a path integral for a master equation.
In discrete phase space? Or the
yes.
one we had?
So discrete phase space is ugly because of this. You can't do this. So you have to find a way to rephrase your master equation in a way which is similar to that, where you have a continuous variable instead of a discrete variable. And that will be our strategy, to find a different representation that allows us to do that. Yeah.
Because so in the path integral we have this action, right? E
Yeah.
minus s, and that's kind of the probability of the entire trajectory under the path integral measure, which is this capital D, right?
Yeah.
So in the master equation framework we have the Gillespie algorithm, which
True.
also gives me the probability of an entire trajectory.
True.
Of course, without the spectral measure, because that's not necessary. So I would expect the analog of a path integral, or at least the action for the master equation case, would be the Gillespie algorithm.
It is one way of representing it. It's a very useless way.
Okay, lovely.
It is a very useful way if you employ it in terms of a simulation algorithm, because it's the most powerful and standard algorithm that you use. And it has the form of a path integral construction. We have used that.
Yeah, it's the same construction.
It's the same logic, but it's not a helpful entity to actually do a field theory with. It's really not. People have tried, I must say, but it didn't turn out to be helpful.
Okay.
And as you will see after the break, the way we phrase it then, the path integral we get, brings it in a form which links it to the other path integral representations that we have for continuous processes. And then you'll see, how much the analogy carries you between a continuous and a discrete process, and where the differences between the two are. They're not the same. I don't know. I did not discuss Kramers-Moriarty expansion, or only shortly, but you may have heard about this. In Kramers-Moriarty expansion, you rewrite a master equation in a form such that you get a Fokker-Planck equation. But you make an approximation. You throw away, lots and lots of terms in the expansion, right? And that means, in general, a master equation is not identical to a Fokker-Planck equation. There may be cases where all the different terms that you throw away in the expansion actually matter. And then you have a difference between a discrete stochastic process and a continuous stochastic process, because the mathematical structures are genuinely different. And that's something we'll see when we derive path integrals for master equations.
So this master equation, you're talking about this integral differential equation, which is a master equation in continuous space.
No, I really mean just a simple master equation with discrete state space, having no continuous part whatsoever, and you rewrite this master equation in discrete space in terms of continuous variables by expanding things in a power series called Kramers-Moriarty expansion, and then you stop at the second order, and the second order expansion is the Fokker-Planck. That's what I mean.
Okay. Yeah, I thought before you expanded that.
Yeah. So let me draw it on the board before we go in the break, and then. Okay. So let's say we have continuous variables. Then you have a Langevin equation for x, and you have a Fokker-Planck equation for p of x and t on some condition, and they are equivalent. Okay. And you know that this is also equivalent to a path integral. So you have all these different formulations that you can tap into when you do continuous variables. Let's just say we have discrete variables. That means we have a master equation. This is for P of n and t, given some condition, some time derivative of that. That's gain minus loss. Okay, and that's the analog of the Fokker-Planck equation. We also have the Gillespie algorithm. Representing that. Then we can approximate that, right? This is not exact, through a Kramers real expansion by a Fokker-Planck equation for considering n approximately a continuous variable. And this is not exact. So once you're there, of course, you know that this is identical to a Langevin equation. And this is identical to a path integral. Because you know that, right? Once you have kind of shifted from a discrete representation to one that's analogous to a continuous representation, you have the same kind of tools and the same kind of analogies. What we ask now is, if you start from here and you derive a path integral, so how do I, well, first of all, we want to know what this is. You know, what's the path integral representation for that? It's valid, strictly valid, for the master equation. No approximations, no tricking, no continuous variable approximation. And then you can ask, is there or is there not a relation between that path integral and the path integral that comes out from the expansion that you have when you do a Kramers-Real expansion? Okay, the answer will be this works sometimes when the effect of the noise is weak and low. It does not work at all if the noise is strong. And the noise having a strong effect is the one example I gave at the introduction, which is the directed percolation case. There, the effect of noise is really, really important and really, really strong. And there's no way of mapping this directed percolation problem onto something that would be equivalent to such a low noise type of approximation. Hope that helps. Yeah?
When introducing the interpretation of stochastic differential equation, we have like different alpha values, and there we assume they should produce the same Fokker-Planck equation, and then we are able to like relate different coefficient A and C. But does it also is it also okay when the noise is so large, then does it mean we wouldn't?
Okay.
It's the same Fokker-Planck.
So the interpretation issue is a representation issue here. Right? So once you are at the level of these Langevin and Fokker-Planck equations, any representation, Ito, Statonovich, Hengi, and whatnot, is okay, as long as you stay within that interpretation. Okay? And that has nothing to do with the question of low and weak, of strong and weak noise. They're very different issues. And one is representation in terms of different mathematics, and the other is actual physics, where the effect of noise may be strong or weak.
But like I would imagine, for example, for a really like delta function like noises, then how we choose the interval would also matters. So
Okay, so here I explained you everything how this works. In the case of a master equation, once you have a master equation, you can also derive, as I said, these kind of Fokker-Planck equations, and the interpretation comes with it. Because you go from a discrete limit and you take a continuum limit, and there's a well-defined order of how you do that. There's no ambiguity once you start from a discrete model. Yeah, you'll see after the break, if we do have time still, how the path integrals here look like. And the issue is really, how should I say? If you take these path integrals and blindly write them as path integrals that you have in the continuum representation, what you get is that your noise becomes imaginary. So you really get nonsensical results if you do that. Meaning there's a real issue, not just an interpretation or representation issue. Different kind of physics that happens. All right, let me take a break. And